Good evening, friends. Welcome to the domain analytics session. So we were looking at legal and law analytics. So we had seen some of the various classification problems. So today we'll be looking at regression analysis and we'll be looking at simple linear regression. So in this, we'll be learning about what is regression analysis, what is a linear model, what is correlation analysis, what is the equation of a straight line, what is simple linear regression, what are transformation, what is bias variance, and a business use case. Okay, so what is regression analysis? Regression is used to study the relation between two variables. Okay, so we'll be having a variable v1 and a variable v2, and we'll be studying how this v1 is related to v2. Basically, one of them will be input and the other one will be output. Okay, so we'll study how change in this variable will also affect this variable. Okay, so we will do this using simple regression. Okay, we will use simple regression if both dependent variable and independent variable are numeric in nature. So both are quantitative data. Only then we can apply this simple linear regression. They should be quantitative data. Okay, both input and output should be quantitative. And if dependent variable is numerical, okay, this is output is the dependent variable. Dependent input is the independent variable. Okay, if output is numerical but the input is categorical, then we will need to use ANOVA. Okay, analysis of variance. Analysis of variance. This method we need to use. Okay, so let us look at some of the examples where we need to use regression. So if we need to find how the IQ affects income or this intelligence quotient, how does it affect income of a person? If we want to find, so here we'll take IQ, this intelligence quotient, as independent variable input data, and income will be the output data, dependent variable. Yeah. Second example, we are testing if hours of work affect sleep or not. If we are working a certain hours of work, will it affect our hours of sleep or not? So we can say dependent variable, this will be output, dependent, and this will be the input variable, independent variable. Similarly, if we test if the number of cigarette smoked affects the blood pressure or not. Okay, so here blood pressure will be output or dependent, you can say. Output or dependent, and cigarette smoke will be input or the independent variable. Okay, so regression analysis, we will draw a chart or a plot between the two variables, dependent and independent variable, to find if there is a linear relationship between them or not, or if there is some relationship between both of them or not. So income to IQ, previous example which we saw, we are plotting here. So y-axis is income, x-axis is IQ. So by this plot, okay, we can clearly say that IQ is directly influencing income, meaning the increase in IQ will also result in increase in income. So we can see it here. Okay. Similarly, if we go for the next example, where we saw chance of heart failure based on body fat percent. Okay. Based on body fat, what is the chance of heart failure? So we see around 0.4, this 0.25 body fat. Okay. 0.25% of body fat if you are having, 0.25 means 25% body fat. We see that it has the lowest probability of getting a heart failure. But yeah, if body fat is around 0.1%, then 0.1, then there is a higher chance of getting heart failure. Also, we can see at 0.4, also there is a high chance of heart failure. So here we can see in this example, the relationship between body fat and chance for heart failure is not linear. It is not linear. And hence it is not sensible to use a linear regression. So linear regression is basically, it will measure in a single line. So here it will not be able to, we can say it will not be able to find this output. Okay, so generally our data is a single line. So it will come something like this. Okay, so it will not be able to tell about this other data, or it will be something like this, and it will not be able to tell about this part of the data. So basically, linear regression will only be able to tell about the linearly dependent variables. So we also, while doing regression analysis, we also look upon correlation. So correlation, we can say it is the relationship or relation between two variables. It is a bivariate analysis, first of all. It is a bivariate analysis. It is a correlation plot, or we can call it scatter plot. Okay, this is a bivariate analysis, and it shows the relation between two variables. Okay, so if we look at this, we can see, if I draw a line, most of the points will lie on this line or lie very close to this line. If this is the case, okay, we call it, first of all, we call it a positive regression, a positive correlation, and we also called it strong because most of the points are lying very near to the line. So it is a strong positive correlation. Why positive? Because with increase in one variable, other variable also increases. Hence, it is a positive. Both of the variables, if they increase together, we call it a positive relation. So it is a strong positive correlation. So here also we can see this is not that strong. Okay, it is a moderate positive correlation. Still it is positive, so moderate positive correlation. Here we cannot find any relation, so this will be no correlation. Now this, we can see there is a negative correlation. Why is this a negative correlation? So with increase in one variable, other variable decreases. Hence, it is a negative correlation. Okay. So we can see also most of the points are not lying on the line. So it is a moderate negative correlation. Here we can see most of the points are lying. So it is a strong negative correlation. And this we can see it is not a linear relationship. This is a curvilinear relationship. So this is correlation, but always remember correlation does not show causation or will not tell you if this is changed, this V1 is changed, will this affect V2 or not? We don't know. Okay. It just shows relation, but causation guarantee is not there. Now this linear regression is based on the equation of a straight line. So equation of the straight line we know it is y equals to mx plus c, where c is the intercept of y-axis, m is the slope, x is the variable, x variable, y is the y variable. So this equation also, our regression line equation is also based on that. So it is nothing but y equals to a plus bx plus e. A is the y-intercept, b is coefficient of x, and e is error. Okay, E is the error term. Now these errors will be having one error for each row, basically. So this each row, if we plot, it should be coming as a bell curve. Okay, it should be normally distributed. Okay, so how can we test this? So very simple, you can do. You can either draw a test plot or a KD, kernel density estimator, or even a histogram. Okay, and after this, we can see if it is having a bell-like shape. We will call this. It is normally distributed. Okay, so we are talking about this equation. So A is the y-intercept, E is the coefficient of x. Okay, y is the dependent variable, x is the independent variable, E is the error. Okay, so our regression will lie on this or depend on this line. Now let us talk about correlation analysis. Okay, so it is the measure of degree of linear relationship between two variables. Okay, linear relationship between two variables it shows. Okay, so if the range of correlation coefficient is between -1 to +1, okay, range of correlation coefficient is between -1 to +1. If it is +1, it is a perfect positive correlation. If it is -1, it is perfect negative correlation. If it is 0, we'll say there is no correlation. Okay, and this is the formula which we have for correlation. Okay, it is nothing but summation of xy minus summation of x into summation of y by root over of n summation of x square minus summation of x whole square, and same for y also. Okay, so if we see this clearly, this will be related to covariance also. So correlation we can say is covariance by sigma x, sigma y, or standard deviation of x and standard deviation of y. Okay, this is the relation between correlation and covariance. Now let's talk something about ordinary least square regression. Okay, so this is an ordinary or very common technique for estimating coefficients in linear regression. Okay, and this relationship between one or more independent variables and a dependent variable. Okay, this is known as ordinary least square regression. So let's see. So this will be so our line starts from here. So wherever it is cutting the y-axis, that will be the y-intercept. Okay, if it cuts at 0, y-intercept will be 0. Now, we can see here we are having an outlier. Okay, these points are not coming up in line. So we are having different outliers. So we are choosing this. Okay. So here we are saying it is an observed value of x, and when x is 0, x is equals to x0 or the mean value. Okay. Mean value is x0 of this line. Okay. If we are having a value on this, we will call this from mean to this point as error term. Okay, and this straight line, this is our regression line, you can say, and it will follow this equation beta 0 plus beta 1 x. Okay, so this is ordinary least square. Okay, now how do we evaluate this? Okay, so to evaluate regression problem, we may either use errors, or R squared value. Now this R squared value is also known as coefficient of determination, and it is nothing but the percentage of output. Okay, percentage of output explained by input. Okay, or we can say percentage of response variable variation that is explained by its relationship with one or more predictor variables. Okay, so a high R square value will suggest that your model is good, better model you are having. If it is between 0 to 100%, sorry, it will always lie between 0 to 100%, and a value between 0.65 to 0.8 is known as a okay relation. If it is more than 0.8, we'll say it has strong relation. Okay, so this is all about R squared. So if we see it this mathematically, okay, SSR is y hat minus y mean whole square. Okay, SSE is y minus y hat whole square. Okay, and SST, SS total is SSR plus SSE, and we are having some measure. So we'll be seeing this. Here only R square is SSR by SST, and SST is SSR by SSE. Okay, next. So here we are talking about confidence interval, prediction interval. So let's see what they are. Prediction and confidence interval are different types of confidence interval used for predictions in linear regression or any other regression problem or any other linear models. Okay. And prediction interval is nothing but it represents a range of single newly observed observation. Okay. And it gives a specified settings of the predictors. Now, confidence interval of a prediction, it represents a range that the mean response is likely to fall given some specified settings of predictors. Okay, so prediction interval is nothing but a range that a single new observation is likely to fall under, and confidence interval is that range where a mean response is likely to fall. Okay, now this prediction interval is always wider than its corresponding confidence interval because we have added uncertainty in predicting a single response versus a mean response. So as confidence uses a mean response, it has narrower, we can say, interval than prediction interval. Okay, next. So we can see here, if y is a continuous value. So in the regression, y should be a continuous value. If y is not a continuous value, it will not come under regression. So y will always be a continuous value. Okay, y is continuous in both cases, you can see. But x can be continuous, cannot also be continuous. If it is a continuous, we can directly apply simple linear regression. But if it is a discrete, then we'll have to create dummy variables. Okay, once this is created, then we go for this linear regression, simple linear regression. Now this error variable. So we were talking about error variable. So there are some requirements which this error variable must fulfill. So error, we can say it is a very critical part of regression. Okay, if this is not a normal curve, then our regression will not be good. So four requirements for error variable calculation are, first of all, the probability distribution should be normal. Okay, mean of the error should be 0. Okay, it is normal, so mean it should be at 0, and standard deviation. Okay, standard deviation will be standard deviation of error for all values of x. Okay, and the set of errors associated with different values of y are all independent. Okay, set of errors. They're having different sets of errors, and whichever errors are associated with different values of y are all independent of each other. Okay, so if we just look at a linear regression flow chart, okay, simple linear regression. Okay, so here what we try to do, we will first train a model. So we are having a data set. We will just take this. We will train a model using ML algorithm. Okay. We'll find the relation between the variables, input and output. So there, simple linear regression will just have one input and one output. Okay. So our input, or we can say it has also been divided into trained test data set. So our trained model Okay, this is the trained model. We are putting machine learning in this, and from this we are getting a relation between the output and input. So this we are getting. Now this we will use on the new data. Okay, new data, unlabeled data will be having. Okay, we need to create its label. So on this data, which is similar to the previous one, okay, we will try to create a label using this mathematical relation. Okay, so on this data, we will predict using this relation. Okay, and we will get some predicted outcome. Okay, so this is how we train our model and test also. Okay, now let us look at a few, not a few, just one use case which we have worked on. Okay, after that we'll be also seeing the coding part of this. So let us go to the use case. So this use case is a Swedish auto insurance problem. Okay, so here this involves predicting of total payment for all claims in thousands of Swedish krona currency given the total number of claims. Okay, so it is a regression problem and it has 63 observations, out of which one input variable we are having and one output variable. The variable names are number of claims which we are taking X, and this will be our independent variable. Independent variable, or we can also call it predictors. Okay, and Y, which is total payments of all claims in thousands of Swedish krona, is our output variable, or we can call this as a dependent variable, or we can also call it as target variable. Okay, so this is our problem statement. Okay, so let's see. So here I am showing you the EDA part. So after doing EDA, we saw we had skewness in our data as well as we had outliers. So as we know, regression problems, regression, they assume that data to be normal. So data should be normal is one of the assumption of a regression problem. Also, this data should be free from outliers. No outliers should be there. Should not have outliers. Errors should be linearly distributed, or error should be normal, we can say. Okay, so these are the assumptions which we need to take care of. So this is not true in our case. This is also not true. So we will do some pre-processing steps. So let's see. So after pre-processing, we are getting histogram to be nearly normal. Okay, and we have also removed all the errors. Noisy data we have removed. Okay, after seeing that, we are getting a linear relationship between the output and input data. Okay, so let us see the code for this. Okay, same problem we'll be doing. So we can see it is a simple linear regression. Okay. And it here we apply the simple line equation. Y is equals to beta 0 plus beta 1 x. Okay. So this shows the relationship between y and x. Okay. And it is a linear relationship. It will be a linear relationship. It will be a line relationship. Because if we compare this with the line equation, it is similar. Y equals to c plus mx. Okay. You can see it is quite similar to the equation of the line. Mathematical equation. Okay. So here also, if we want, we can use an error term. Okay. So C will be equals to beta 0 plus error if we consider that. Okay, so let's see the Swedish auto problem. So Swedish auto insurance data set, it has, so it is involving predicting of total payment of all claims. Okay, payment of all claims in thousands of Swedish krona. And we are given the total number of claims. Okay, it is a regression problem, so we will be applying simple linear regression. Now this is comprising of one input variable and one output variable, just one input and one output we have, and the variable names we have already seen the same thing in the slides also. So here you can see we are importing pandas as PD. This is, you can say, it can be used for data manipulation. Then I have loaded the data set insurance.csv. Okay. Then I am looking at the head of the data. So first 10 rows I am looking at. So these are the values you can see. Number of claims 108, kroner 392.5. Number of claims 19, 46.2, 13, 15.7. Okay, these are the values we are having. Okay. Now I'm just describing the column. So describe gives us the count, the mean, the standard deviation, and the quantiles. Okay. So these are the values we are checking here. So you can see count is 63 number of rows we are having. Mean you can see it is 22.9. This is 98.1. Standard deviation 23. It is 87. Here minimum value is 0. We can call it the minimum quantile. 25th quantile is 7.5. This is 38.8. 50th quantile 14. This is 73. 75th quantile 29. That is 140. And max value we are having 124. And here 422. Next, we are checking for the info. So info is a function which gives us many information about the data. So it gives us the name of the columns first, name of columns. Then it gives us count of the columns. Then it also gives us whether the columns are having null values or not. It also tells us about the data type. Okay, so you can see all of this data we are getting: number of columns, count, null or not null, and data type. Okay, so we need to now inspect the data and do exploratory data analysis and Then we also need to remove any anomalies like missing value, invalid values. Okay. So let's see. Okay, so we will need to perform a visual exploratory data analysis. For that, we'll be drawing histogram and box plot. Okay, we are conducting visual exploratory data analysis on the data set using histogram box plot. So histogram is used to give us the data distribution. Okay, and box plot will give us outliers. Okay, so here we are trying to find the correlation between two variables. Okay, the variables are number of claims and payment of all claims. So we'll make a scatter plot also between them. We'll see this, and also we'll try to compute the correlation coefficient. So let's see. So first of all, I'm doing this matplotlib as PLT. I'm importing matplotlib, and I'm drawing the histogram and box plot for all the rows. So here we are, all the columns. So here we are having just two columns. So we are getting only two diagrams. Box plot also same way. We are drawing for both the columns. So you can see. So from this histogram, we can see that this is having positive skewness, or it is right skew. Okay, so we need to make this data normal, otherwise we cannot work on this. So we'll try to make this normal. Also this output also we can see it is right skew. So we'll also try to make this also normal. Okay, next we can see outliers present in the box plot. Okay, there are outliers. So both we need to treat the outliers as well as we need to make the data normal. So let's see how can we do that. So for outlier treatment, we will be doing winsorization. So this is a replacement method. So basically outlier treatment, if we are going to do, either we can remove it completely, or we can replace it, or we can retain it. Okay, so here we decided to replace the value. Okay, so I am replacing the values using IQR, so maximum value. So as it is above, you can see above the maximum point, so it will be converted into a max value. Okay, whatever max value in the data we are having, that value will be assigned to these outliers. So let's see. So first I'm doing winsorization. Okay, I have done winsorization. Then we are also doing transformation. Okay, so you can see before transformation this was the skewness. Now after transformation we are getting near zero skewness. Before transformation we had one skewness. Now after transformation we are getting 0.1. Okay, so we can also see after transformation we are getting normalized histogram, and outliers are also gone. Okay, we can see outliers also we have treated. Next we are finding the correlation coefficient between the two of them. Okay, So we can see correlation coefficient is 0.877. I'm getting this value between the two. We are getting the correlation coefficient 0.87. Means 87% correlation we are finding it. So yeah, it is having a strong correlation, we can say. So next I am drawing the scatter plot. Okay, from scatter plot also we can clearly see there is a linear relationship, but we cannot say it is a good linear relationship. We can just say it is moderate strong relation, moderate relationship here. Moderate relation we are having. Okay. So up to this, we had done the EDA part. Okay. Next coming, we will have to also make a prediction model. For this prediction model, we need to first train. We need to first train the model or train the ML algorithm and fit it on the dataset, train dataset. Okay. Once this is done, ML model, from this we'll be getting the mathematical equation. Okay. And we'll use this to predict on new values. Okay. So basically this will be converted into a machine which can predict new values. Okay. So let us see. So on that, I have taken the variable names x as the independent variable, which is the number of claims, and y as the dependent variable, which is also known as total payment of all claims in thousands of Swedish krona. X, you can see I'm taking DF insurance, number of claims, and y I'm taking DF insurance, payment of all claims in Swedish krona, and I'm just now printing what is x shape, and what is x and dimension. So let's see. So you can see this is the value of x. Okay, these are all the values of x we are having, and shape is 63. So total number of rows we are having 63, and based on that also here we are having 63 data points, and dimension is 1. So it is a one-dimensional array basically. Okay. And I am just reshaping it to a 2D array, two-dimensional array. So here we can see I am printing the x, then x shape, then x dimension again after reshaping. So let us see. Just a second. Okay, so this is an array which we have built. You can also see we are having 63 into 1. Okay, so we have converted this into a two-dimensional array, so we are getting the value 2. Once this is done, now we will split the data into train test. Okay, for that, first I'm loading the linear regression module from sklearn linear model. Okay, and also I'm loading from sklearn model selection train test split, which will be used to split the data. Okay, so this x and y will be split into x train x test, y train y test. So we are doing accordingly. Okay, so here we are dividing x into train and test. Okay, y also is divided into train and test. Now we are training the linear regression model. So here I'm initializing it. Okay, so up to this it is initialization. Once this is done, we can fit it on the model. So I'm fitting it on the X train and Y train, which is the input and output value. So it will be trained on this. Once this training is done, now it is ready to predict. Okay. So print slope, then this format reg coef. Okay. So here the value of coefficient will be put, and here the value of intercept will be put. Okay. So what is coefficient? What is the intercept? If you remember the equation, y is equals to beta x plus beta 1x plus beta 0. So this is the we can say intercept, and this is the coefficient. Okay. So from this equation we are finding these values. So here we are looking at the values. So slope I am getting 1.8, intercept we are getting 1.12. Okay. So up to this we are training our model. Training has been done now. Okay, next we'll be making prediction on the test data set. Test set which we previously splitted with from the one final one. So here we are saying y pred equals to reg dot pred x test. Okay, we are predicting on x test. So I'm running, I run this. Okay, then we are predicting on a value 56. Okay, so for 56 claims we are getting 103. So let us look at our data set if we can find something closer. 56. So 56 you can say we are having 57 here, it is 170. So if we go back and see the value, okay, there it was 170, but here generalized we are getting 103. Okay. Now from this we need to find the accuracy of our data or our model. Okay. So we are calculating this using mean squared error MSE and also R squared value. R square, it is also known as coefficient of determination. We discussed this. Okay. So this will be finding out R square and MSE. MSE is mean squared error. Okay. So we'll find this. And after finding, we are getting mean squared value is 5.0, which is an okay value. And coefficient of determination or R square score, we are getting 0.69 or 0.7. Okay, this is also an okay value. So we are not getting that good prediction, but yeah, we are getting an okay prediction. 0.7 is an okay value. So we'll be going with this model. So basically, let me summarize. Okay, so we can say this regression analysis. Okay. Just a second. Yeah, this regression analysis. Okay, it is just an estimate of an unknown effect of changing one variable okay, changing one variable, how it affects the another variable. So we'll be estimating this here. Okay, and here we also look at the linear relationship y is equals to beta 0 plus beta 1 x. Beta 0 is the y intercept, beta 1 is coefficient, or if we compare this with the simple line equation, it will be the slope. Okay, and here we try to find this linear relationship. So our data, if it is like this, we can say this is a linear equation problem. But if our data is something like this, non-linear data, we cannot summarize that data using this linear regression. Okay, so friends, that was it for today. Will be so tomorrow we'll have our last session. It will be on neural networks. So we'll be seeing this tomorrow. So yeah, thank you friends. Have a good day. We'll be closing our session now.